The prototype sat on the testing bench in Zella Malis, Thuringia, in the winter of 1938. It didn't look like the Luger P08 it was meant to replace. Where the Luger had graceful lines and a toggle mechanism that moved like clockwork, this new design, designated the Heeres Pistole or army pistol, had an exposed barrel, a squared slide, and a utilitarian profile that suggested function had won every argument with form. Fritz Walther stood near the bench, watching as military evaluators examined the pistol. They turned it over in their hands, tested the weight distribution, and cycled the slide. Walther knew what they were thinking. This didn't have the prestige of the Luger. It didn't have the same visual elegance, but elegance wasn't what the German military needed anymore. The Luger had been designed in an era when pistols were officers' sidearms, symbols of rank and precision instruments produced by skilled craftsmen. But the world had changed. The era of massive global struggles had shown that modern tension consumed material faster than peacetime manufacturing could sustain. Production capacity, not perfection, would define the next generation of military equipment. The evaluators field-stripped the prototype. No tools required, just hands. Slide off, locking block out, barrel forward, recoil spring assembly removed. 30 seconds. They reassembled it in less time. One officer, a veteran of the difficult Eastern campaigns in the previous era of unrest, nodded slowly. He'd seen what happened to complicated mechanisms in mud, snow, and freezing cold. Walther had built his career on understanding what users actually needed. His sporting rifles and target pistols had earned respect across Europe, but military adoption was different. It wasn't about what worked on a range in good weather. It was about what worked when everything else had failed. The P38 designation would come later, after modifications and trials. But the core principles were already locked in place. The double-action trigger, revolutionary for a military pistol, meant personnel could carry it safely with a round chambered and the hammer down. The decocking lever eliminated the risky practice of manually lowering a cocked hammer on a live round. The loaded chamber indicator gave visual and tactile confirmation of the equipment's status. These weren't features added for marketing. Each one addressed a documented failure mode from the previous generation of designs. Walther had studied reports of incidents, field assessments, and armorer complaints. The P38 was an answer to real problems, not theoretical improvements. The testing officer set the pistol down and made notes in his evaluation folder. Walther couldn't see what he was writing, but the fact that the examination had lasted this long was itself encouraging. Poor designs were dismissed quickly. This one was getting serious consideration. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Fritz Walther's factory in Zella Malis had been producing equipment since 1886, when his father Karl established the business. By 1938, the company had built a reputation for quality sporting items and target pistols. But military contracts were different. They meant survival or extinction for a manufacturing concern in the years leading to another major international crisis. The authorities had been testing designs since the early 1930s, looking for a Luger replacement. Walther wasn't the only manufacturer competing for the contract. Mauser, the company that produced the Luger under license, had its own designs. So did Sauer and Sohn. Each company knew that winning meant guaranteed production for years. Losing meant watching competitors expand while your factory sat underutilized. Walther faced specific constraints. His factory couldn't rely on the ultra-precise machining that made Lugers expensive and time-consuming to produce. He needed a design that could be manufactured with more stamping, more modular assembly, and more tolerance for the type of workforce available if production scaled to high levels, which everyone knew was coming. The double-action mechanism wasn't new, but it was uncommon in military equipment. Most forces preferred the simplicity of single-action designs, but Walther understood that simplicity in mechanism didn't always translate to simplicity in use. A single-action design required the operator to manually cock the hammer or carry it cocked, both problematic in different ways. He'd tested various trigger mechanisms on sporting models for years. The challenge was adapting double action to a locked breech military pistol that had to fire powerful 9mm parabellum ammunition reliably. The trigger linkage had to be robust enough to survive hard use, but precise enough to function smoothly. The locking mechanism itself drew from Walther's earlier designs, particularly the PP and PPK models. But those were blowback designs for smaller cartridges. The P38 needed a locked breech. The barrel and slide had to stay locked together during the firing cycle to handle pressure, then unlock to allow cycling. Walther chose a falling locking block. It was simpler than toggle systems, more reliable than rotating barrel designs, and manufacturable with existing equipment. During the cycle, the block wedged between barrel and slide, keeping them locked. As the slide moved backward, a cam path forced the block downward, unlocking the system and allowing the barrel to stop, while the slide continued rearward to extract and eject the spent case. Testing revealed problems. Early prototypes had issues with the locking block's durability. The angles had to be precise, too shallow, and the lock was weak, too steep, and the mechanism bound up. Walther's engineers adjusted the geometry, refined the metallurgy, and tested again. Military evaluators visited the factory regularly. They brought lists of requirements, some written, many verbal. The equipment had to work in temperature extremes. It had to function with dirty ammunition. It had to survive being dropped, dragged, and generally abused in ways that would horrify a sporting enthusiast. Each requirement drove design decisions. The external hammer wasn't just for double-action functionality. It allowed visual confirmation of the equipment's state. The loaded chamber indicator wasn't decorative. It could be felt in darkness. The decocking lever wasn't for convenience. It was for safety when an operator needed to quickly make the item safe, but didn't have time for careful manipulation. The heart of the P38's design was elegant in its directness. When a round was chambered and the trigger pulled in double-action mode, the trigger bar pushed the hammer back against its spring until it released, falling forward to strike the firing pin. The firing pin drove into the cartridge primer, igniting the propellant. Internal pressure built instantly, over 35,000 pounds per square inch. This force pushed in all directions, forward against the cartridge case, backward against the bolt face, and outward against the chamber walls. In an unlocked design, that backward force would slam the slide rearward uncontrollably. The locked breech system prevented this. The locking block sat between the barrel and slide, wedged into place by geometry. As pressure built, the barrel and slide wanted to separate, but the block's position made this impossible. The entire assembly, barrel, block, and slide, moved backward together for approximately 4 millimeters. This short distance was critical. During those few millimeters of travel, the locking block rode along a cam track machined into the frame. The track was angled downward. As the assembly moved back, the track forced the locking block to drop, pivoting it out of engagement with the slide's locking recesses. By the time the block dropped clear, pressure had fallen to safe levels. The projectile had exited the barrel. The barrel stopped against the frame, but momentum kept the slide moving rearward. The extractor claw hooked the spent case and pulled it from the chamber. As the slide reached its rearmost position, the ejector struck the case base, sending it out through the ejection port. The recoil spring, compressed during rearward travel, now pushed the slide forward. On its forward journey, the slide stripped a fresh cartridge from the magazine and drove it into the chamber. The barrel remained stationary during this process. As the slide reached full battery, the locking block was forced upward by the same cam track, this time acting in reverse. The block rose into its locking position between barrel and slide. If the trigger had been released after the first cycle, the hammer remained cocked and the next trigger pull required only light pressure, single action mode. If the trigger remained depressed, it would cycle again immediately upon reaching full battery. This was the machine logic of controlled repetition. The decocking lever added a layer of safety. When rotated, it blocked the hammer's forward travel while simultaneously releasing it from engagement. The hammer fell under control of the lever, coming to rest safely against a blocking surface that prevented firing pin contact. The operator could then release the lever, leaving the equipment in double action mode, but completely safe, even with a round chambered. Every surface that made contact during this cycle had to be heat-treated for hardness, dimensioned for correct cam action, and positioned with enough precision to function, but enough tolerance to survive harsh conditions. The tolerances were measured in hundredths of millimeters, tight enough to function correctly, loose enough to work when dirty. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The Walther factory conducted testing that went beyond standard requirements. Test units were subjected to overpressure cartridges deliberately loaded to extreme levels. They were used for thousands of cycles without cleaning. They were frozen, heated, submerged, and tested again. Each failure revealed a weakness to address. Early test results showed accelerated wear on the locking block. The metallurgy wasn't quite right, the steel was too soft and began to deform after extended use. Walther's engineers experimented with different alloys and heat treatment processes. They settled on a higher carbon content and a specific tempering procedure that gave the block the hardness it needed without making it brittle. The firing pin spring presented another challenge. It had to be strong enough to ensure reliable ignition, but not so strong that it slowed the firing pin's retraction, potentially causing unintended activation if the item was dropped on a chambered round. The solution involved a two-stage spring design that provided adequate energy while maintaining positive return action. Magazine feed reliability consumed significant testing time. The P38 used a single-stack 8-round magazine, simpler and more reliable than double-stack designs, but requiring the correct feed lip geometry and follower design. The lips had to guide cartridges at the precise angle to ensure smooth feeding. Too steep and rounds jammed, too shallow and they caught on the chamber mouth. Walther tested with ammunition from multiple sources. Military logistics meant the equipment would use whatever ammunition was available, and different manufacturers had slight variations in dimensions and case hardness. The P38 had to function with all of them. Environmental testing revealed issues with the safety mechanisms. In extreme cold, lubricants thickened, and the spring that controlled the block's movement became sluggish. Walther reduced the spring tension and polished the contact surfaces to reduce friction. The modification worked. The equipment functioned reliably, even in sub-zero temperatures. Evaluators brought P38 prototypes to proving grounds and tested them alongside competing designs. They used them in dust, rain, and snow. They deliberately induced malfunctions to see how easily operators could clear them. They timed how long it took to disassemble and reassemble the equipment with cold, gloved hands. The exposed barrel design that seemed like a cosmetic oddity proved functionally superior. Because the barrel didn't move during the extraction and ejection cycle, accuracy was more consistent than in designs where the barrel tilted or rotated. The short recoil distance before unlocking meant the sight picture was disturbed less than in other systems. Walther made dozens of small refinements based on testing feedback. The hammer spur was reshaped for easier manual cocking. The safety lever's position was adjusted for more positive engagement. The trigger guard was enlarged to accommodate gloved fingers. The front sight was strengthened after several broke during rough handling tests. By late 1938, the design had stabilized. The formal designation Pistole 38 was assigned. Production tooling was ordered. Factory workers began training on the manufacturing processes. What had started as a prototype on a testing bench was becoming a standard military sidearm. The detail that explained everything about the P-38's design philosophy emerged from a maintenance manual prepared for technicians. Under the section describing complete disassembly, the instructions revealed something remarkable. Every pin, spring, and component could be removed and replaced without specialized tools. This wasn't typical for military equipment of the era. Most required specialized kits, punches, drifts, and unique wrenches. The P-38 was designed around the assumption that somewhere, at some point, an individual would need to completely disassemble this item in conditions that ranged from merely inconvenient to actively hostile. The slide stop pin could be pressed out with a fingertip once the slide was removed. The locking block pin was spring-loaded and could be pushed out with light thumb pressure. The trigger mechanism used crosspins that were sized to be removed by hand, but tight enough not to move during use. Even the grips were attached with slotted screws that could be turned with a coin or cartridge rim if a screwdriver wasn't available. This design choice cascaded through every aspect of the item's construction. Parts couldn't be fitted to individual units. They had to be interchangeable. An operator couldn't rely on having the right replacement part for his specific serial number. He needed to be able to grab any P-38 part from a bin and have it work in his equipment. Interchangeability drove manufacturing tolerances. Parts had to be loose enough to interchange, but tight enough to function correctly. Finding that balance required a sophisticated understanding of the tolerances each component actually needed versus what traditional craftsmanship assumed was necessary. The metallurgy reflected this philosophy. Rather than using hand-fitted parts made from extremely hard steel, Walther chose steels that could be machined more easily, then heat-treated to achieve adequate hardness. The locking block, barrel, and slide received intensive heat treatment. The frame, grips, and smaller components used less expensive processes. Manufacturing methods combined traditional machining with newer stamping techniques. The frame was milled from forgings, more expensive than stamping but more durable. The trigger guard and magazine catch used stamped components. The grips were molded plastic, revolutionary for the time but practical for mass production. This modular, tool-free design meant that damaged components could be swapped in minutes. A broken firing pin didn't require a specialist, just a replacement part in 30 seconds. A worn recoil spring could be changed in the field. Even the locking block, subject to the most stress, could be replaced quickly if it showed excessive wear. The loaded chamber indicator exemplified this philosophy. It was a simple pin that protruded from the slide when a round was chambered. It could be seen and felt even in complete darkness. If it broke, it didn't disable the equipment. It just removed a convenience feature. It was held in place by spring tension and could be popped out and replaced without tools. Every design decision in the P-38 reflected this central principle. The equipment had to survive, not just active use, but everything that happened in between. It had to work for personnel with minimal training, in environments that destroyed complex mechanisms, maintained by tired individuals with cold hands and no workbench. The P-38 entered production in 1939, just as the massive struggle that would define the 20th century was beginning. Over 1 million were manufactured during that period by Walther and 2 other contractors, Mauser and Spreewerk. Each manufacturer was identified by a code stamped on the slide, AC for Walther, BF for Mauser, CQ for Spreewerk. After 1945, production continued under different circumstances. Authorities confiscated the machinery and produced P-38s under the designation Model 1950. The design was sound enough that it transitioned directly from wartime manufacturing to peacetime production without fundamental changes. In 1957, the newly formed Bundeswehr West Germany's military needed to re-equip. Rather than designing something entirely new, they returned to the P38. Walther resumed production of what was now designated the P1, using aluminum alloy frames instead of steel to reduce weight. The fundamental design remained unchanged because it didn't need to change. The P38's influence extended beyond direct production. Its double-action, single-action trigger system became the standard for military and police models globally. The Beretta 92, Sig Sauer P226, CZ75, and dozens of other designs adopted variations of the P38's trigger mechanism. The exposed barrel, initially seen as unusual, became common in later designs once engineers recognized its benefits. What Fritz Walther understood in 1938 was that military equipment needed to be designed for reality, not ideal conditions. Ranges and testing facilities had controlled temperatures, clean ammunition, and skilled operators. Harsh environments had none of these. The P38 was engineered for the field, not the range. This meant accepting that the equipment would never be as beautiful as a Luger, never as refined as a custom target item, and never as prestigious as handcrafted pieces. But it would work. It would work when dirty, when cold, and when maintained by someone who'd never seen the inside of such a mechanism before. It would work because every component was designed to be replaceable, and every assembly was simple enough to be performed by feel in darkness. The engineering philosophy wasn't revolutionary in concept, designing for maintainability and reliability instead of perfection. But applying it comprehensively to a military sidearm required Fritz Walther to make hundreds of small decisions that collectively defined a different approach to design. The P38 remained in production until 2000, when it was finally replaced by newer designs. 62 years of continuous production and service, millions of units manufactured, decades of field testing under every conceivable condition. The design endured not because it was perfect, but because it was honest about what perfection meant in practical terms. That tool-free disassembly requirement, the ability to completely strip the equipment in 30 seconds without any implements, that single design constraint explained everything. It meant every other decision flowed from understanding what operators actually faced. It meant the entire system was conceived to survive human factors, not just mechanical stress. Fritz Walther's achievement wasn't creating the most advanced design of 1938. It was creating something that would still be relevant in 2000, because he designed for problems that don't change: mud, cold, fatigue, and the need to repair things when everything else has failed. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.